While discussing the transfer characteristics of an operational amplifier, I have told you that an operational amplifier has three regions of operation: positive saturation and negative saturation region. In between there is a linear region. Now I will show you some application of operational amplifier linear region. In this video I will show you how we deduce the output voltage equation of in case of inverting and non-inverting amplifier. So let me show you at first the inverting amplifier. This amplifier will use the negative feedback. Okay, so look at this circuit. This is the arrangement of negative inverting amplifier circuit of an operational amplifier. This is a negative feedback op-amp because this output is directly connected with the inverting terminal through a feedback resistor, and our sole purpose will be to find the equation of this output voltage and the ratio of this output voltage and this input voltage to deduce our desired gain of the operational amplifier. Let me show you. In this amplifier we will apply the input voltage to the inverting terminal. See, this is the inverting terminal and we are applying input voltage through a series resistor R1 in the inverting terminal, and the output voltage, okay, this output voltage will be 180 degree out of phase with this input. If I let's say apply a sinusoidal whose positive cycle starts at t equal to 0 at the inverting terminal, I will get an output of same shape, but it will be 180 degree out of phase with respect to this input voltage. 180 degree phase shift means that it starts its positive cycle here at t equal to 0. It will start its negative half cycle at t equal to 0. This is the t equal to 0 point. Now let me derive the equation of this output voltage. Okay, this is our inverting terminal and this is our non-inverting terminal. Non-inverting terminal is directly grounded. Okay, therefore Vp equal to 0. When we connect any terminal with ground, as ground has a potential of 0 volt, it will this terminal to ground potential will be also 0 volt. And in case of negative feedback, I have shown you Vp, this non-inverting terminal voltage and this inverting terminal voltages are equal, so I can write Vp equal to Vn. As Vp equal to 0, consequently our Vn will be equal to 0. Now let's say the current that is flowing through this R1 is in this direction and that current is I1. The current that is flowing in this direction is I2. As an operational amplifier has very high input resistance, therefore the current through this terminal will be equal to 0 ampere. Okay, so there are three components of current. First one is the current through this R1, second one is the current through this inverting terminal which is equal to 0, and third one is the current through this feedback resistor which is equal to I2. Now I will apply Kirchhoff's current law to this inverting terminal. What is Kirchhoff's current law? Incoming summation of incoming current equal to summation of outgoing current. Therefore here only incoming current is I1 and outgoing current is this 0 ampere and this I2. So I can write, if I apply Kirchhoff's current law to this inverting terminal, I can write I1 equal to I2 plus 0. Now see, what is I1? I1 is the current that is flowing through this path. As you know, current always flows from higher voltage towards lower voltage. Therefore, if I want to write down the equation of I1, I will take the voltage difference at this terminal and this terminal, which will be Vi minus Vn, and divide this voltage difference with this R1. This R1 is the which is our Ohm's law. The current through this path is 0 and the current through this path is flowing in this direction. So this terminal, as current is flowing in this direction, that means this terminal is at higher potential, this terminal is at lower potential. So voltage difference will be Vn minus Vo divided by this resistance, Ohm's law. I equal to voltage difference divided by simple resistance. Higher voltage minus lower voltage, this is higher voltage, this is lower voltage. So I can write Vn minus Vo divided by this Rf. Now if I look at this Vn equal to 0 as Vp equal to 0, as the circuit is in negative feedback, so I can write Vi minus 0 divided by R1 equal to 0 minus Vo divided by Rf, and after rearranging this equation I will get Vo equal to minus Rf divided by R1 into this Vi. This equation is called the output voltage equation in case of inverting. So this voltage Vo is the output voltage equation of inverting amplifier. Now we know that gain equal to output voltage divided by input voltage. So if I take this Vi in the left side, I will get Vo divided by Vi equal to minus Rf divided by R1. So this is the gain of minus Rf divided by R1 is the gain of this inverting amplifier. And see, this minus sign signifies that the output voltage will be 180 degree out of phase with respect to input voltage. Okay, after that I will show you another linear application of operational amplifier, and that is non-inverting amplifier. So why this amplifier is called non-inverting amplifier? At first this amplifier will also use negative feedback. See, this is the circuit arrangement. See, this is the circuit arrangement of non-inverting amplifier, and this circuit will also use negative feedback. Output is directly connected with the input voltage. Okay, sorry, the output is directly connected to the inverting input terminal. So this is a negative feedback. Why this is called non-inverting amplifier? The input voltage is applied to the non-inverting terminal. See, this Vi is applied to the positive or non-inverting terminal of the operational amplifier, and output will be in phase with the input voltage. Let's say if I apply a sinusoidal voltage of this shape here, I will get the same output voltage of same shape at the output terminal. Okay, now let me, here we will also derive the equation of this output voltage and the gain, the ratio of Vo divided by V, the ratio of Vo and Vi, that is gain. Okay, so at first look at this terminal. Let's say the current that is flowing through this R1 is I1, and the current that is flowing through this RF is I2. As the op-amp input has high resistance, therefore the current through this path will be equal to 0 ampere. Now see Vp, what will be the Vp? In this case Vp is the voltage difference across this terminal and this terminal, therefore our Vp will be equal to our input voltage. And second one is that op-amp, the negative feedback makes this output voltage, sorry, the negative feedback makes this Vp and Vn equal. So I can write Vp equal to Vn equal to our Vi. Okay, here non-inverting terminal is connected to input voltage, so Vp equal to Vi, and in case of negative feedback Vp equal to Vn, therefore Vn will be equal to Vi. After that I will apply Kirchhoff's current law to this inverting terminal. Kirchhoff's current law means that there will be three currents. One is this incoming current at this inverting terminal, and two outgoing current from this inverting terminal. So summation of incoming current I1 will be equal to the summation of outgoing current, 0 plus I2. Okay, 0 plus I2. Now what is the current? I1. See, this R1 is directly connected to this ground, and the ground has a potential of 0 volt, and this terminal has a potential of Vn. We don't know the value of Vn, Therefore, as the current is flowing in this direction, that means I have to assume that this 0 volt is higher than this Vn. This is the convention of current flow. Current will always flow from higher voltage to lower voltage. So I will write 0 minus Vn divided by R1, and through this RF current is flowing in this direction. So this terminal will be at higher potential and this terminal will be at lower potential. Vn minus Vo divided by this feedback resistor Rf. Okay, now we know that Vn equal to Vi. Here Vn equal to Vi as Vp equal to Vn. So I can write minus Vi divided by R1 equal to Vi minus, this is Vi, minus Vo divided by Rf. If I rearrange this equation, I can write, if I cross multiply, then I will get minus Vi Rf equal to R1 Vi minus Vo R1. So from here I can write Vo R1 equal to Rf plus R1 into Vi, which will eventually give us Vo equal to Rf plus R1 divided by R1 into Vi. So I can write, so this is the output voltage equation of inverting amplifier. So this is the output voltage equation of non-inverting amplifier. If I take the ratio of Vo and Vi, I will get Vo divided by Vi equal to 1 plus Rf divided by R1. As you know, the ratio of output voltage and input voltage is the gain of the operational amplifier. So I can write gain equal to 1 plus Rf divided by R1. Rf divided by R1. See the output, look at the equation of output voltage. When we take the negative feedback, the gain is totally independent of the operational amplifier. Rather, it depends on the feedback resistor and the bias resistor R1. Now look at the gain equation of this operational amplifier. See, gain equal to 1 plus Rf divided by R1. In case of ideal operational amplifier, gain is infinity, and this gain does not depend on the other circuit parameter. It is always assumed to be infinity. But when we connect an operational amplifier in negative feedback, the gain is totally depending on the circuit parameter. How do we choose the value of feedback resistor and the bias resistor? This gain equation has a special application. Let's say if I connect the output terminal with the inverting terminal with a short circuit, that means Rf will be equal to 0 ohm. If Rf becomes equal to 0, this gain will be equal to 1 plus 0, which is equal to 1. That means this non-inverting amplifier will be also an amplifier, but it will have a gain equal to 1, and this type of operational amplifier is known as voltage follower or unity gain amplifier. Okay, that's it. Thank you.